And the other special case is, or the very first special case is, if these experiments are independent, right? Then what you can write? Then you can simplify this. So, if the stochastic process is independent, then essentially this probability that you are looking at right, it should just be product of probabilities. That is what independence means, right. So, independent stochastic process has this product probability, general stochastic process has this ordered conditioning, and then you take the product. So, based on this, we will study a very nice and specialized stochastic process which is called a Markov chain. So, Markov chain is a process where xk is independent of xk minus 2, xk minus 3 dot dot x1. So, it may depend on the previous one, immediate previous, but not the history, okay, not anything before the previous. So, that is the probability of xk being little xk given the previous ones. This probability is just the same as this one, okay, xk minus 1. So, probability of small xk coming may only depend on little xk minus 1 and nothing that precedes, and this is true for all k greater than equal to 2 and all x1 little x1 to little xk in the domain in the state space. Okay, if this happens for all possibilities, then you say that it is a Markov chain or a Markov process. So, remember this means may depend on xk minus 1. That is what we really meant. Okay. So, it is clear that independent process is also a Markov process. So, independent random variables they do form a Markov chain. because not only xk minus 2, but everything that comes before xk is independent of, right. So, the condition is satisfied. So, independent random variables do form a Markov chain, but are there more interesting examples? So, let us see one. So, toss a coin many times. So, obviously, these will be independent events, but you are interested in counting how many heads you saw till the ith toss. So, let xi be the number of heads till ith toss. Okay, for all I at least 1. So, what you can show is probability that xi is small xi given the previous things, you can see that this all that matters is I minus 1, not the whole list. Right. So, think about this. So, the reason is that once you know the count, if you know the count up to I minus 1 of heads, then the ith count just depends on your current flip, the current toss, right. It does not matter what happened in I minus 2, I minus 3 and so on. So, just from the previous number of heads you have to add the current experiment value, whether it is 1 or 0. So, it just depends on the previous count, right, which in any case is half, right. So, no matter what the count was before, the count not changing means that you are tossing a tail, you get a tail, and the count increasing means that you got a head. So, this will actually be equal to half if xi is xi minus 1 or plus 1. So, let me write it like this. Okay, either you are asking for one more or you are asking for no change, else it will be 0. Right. So, if you are asking for a change of 2 heads, then it is not possible, and if you are asking for a change of minus 1 head, then that is also not possible, right. So, the probability only depends on the previous, which means that this is a Markov chain. Is a Markov chain. So, an interesting and very simple Markov chain is just counting the heads. Okay, keep tossing coins, count the heads, and these random variables, they form a Markov chain, and there is some dependence on the previous value. That is a good example to keep in mind. In fact, it has one more property, it is homogeneous. So, what is that? So, let us define it. So, we call process homogeneous Markov chain if the conditional probability does not depend on time. So, let me clarify this. In terms of formula, what we are saying is probability of xk being a value given the previous value so after j getting an I, it does not depend where in the process you are asking the question. So, this is equal to the very first. Okay, from the initial configuration, this big X 0, if that was j, what was the probability next time you got I? This probability does not change if you look at xk on xk minus 1. Okay, so, in this case we call the Markov chain to be homogeneous, and this example of coin toss actually satisfies this, right, because you look at the values, this half and 0, they really do not depend on I, they just depend on what the difference of the values is. So, this is a very nice example, it gives you really the meaning of all these definitions that today you have seen. Okay, so let us now prove a more general theorem. Which will justify or which will explain to you why the coin toss example is so nice. So, this says that if you actually take independent random variables so if xi are independent random variables, then take their sum, okay, the initial sum. So, j going from 1 to I. So, these yi's are now just taking a sum of these of the first 0 to I ones. So, it is a new process, and this is a Markov chain. Okay, this is why the coin toss example worked, because you were getting heads and then you were taking actually sum of the Bernoulli random variable. And second is about homogeneity of this. So, if xi are identical, so they are independent, identically distributed, okay, so this is called IID. Okay, independent and identically distributed. So, if xi's are IID, then these yi's, this is actually a homogeneous Markov chain. Okay, so this is a generic way of constructing Markov chains and their homogeneous versions. You either take independent random variables or you take identically distributed ones and independent. That is why the coin toss example is a generic example. So let's quickly prove this. The proof is now quite easy. So in the first case, what is the probability of yi being small yi given the previous ones? So remember how we defined y, that was a sum, right? So given small y1 to small yi minus 1, all that matters is what is the probability of this last random variable being this, right? It all matters. So this is all that matters, which is also what we did, remember, when we analyzed this number of heads example, right? We looked at the difference. So that is all that matters, and which is something equal to only the previous. Right? From small yi minus 1, how do you go to small yi? So which means that it is a Markov chain. So that is done. Let's move on to the second one. So in the second one, this probability, since we have assumed identical distribution, so this will be equal to probability of, in fact, x1 being this value, right? Why? Because probability of xi being any value, in fact, probability of xi being value epsilon is the same as probability of x1 being epsilon, right? This I doesn't matter. So from that, so this previous probability is actually equal to, is the same as x1 taking this, which is equal to y1 being small yi and y0 being small yi minus 1, right? Which means homogeneity. So that was simple, almost, from the definition. So we are studying homogeneous Markov chain for two reasons. One is that many physical examples actually follow this, and second is that it will be easy to represent and analyze. Okay, so why? So let me first give a alternate representation of it. So representing in a figure. So suppose you have a Markov chain where a homogeneous Markov chain where the state space has 3 entries A, B, C. And the transition probabilities like probability to go from value A to value C, okay, from x0 to x1. So then you can represent it like this: A, B, C are the elements in the state space. You go from A to B, B to A, Okay, these are all the ways in which the process can move A to B or B to A, then A to C, C to A, and B to C and C to B. And for example, this A to C transition, this happens with probability TAC, and this C to B happens with probability TCB, and B to C happens with TBC, and so on, right. So, all these probabilities may be different, and this is how you can represent a homogeneous Markov chain. And given this picture, then you can see the evolution of the chain up to infinite time. So, with this picture in mind, it may not be easy to work with pictures. So, we will instead work with matrices. Okay, so alternatively, in fact, even equivalently, we use matrices, and let us define that. So, T is an S cross S matrix, entries in, they will be probability. So, 0 1, this real interval. So, ijth entry is probability of going from value I to value j. So, T is the transition matrix of a homogeneous Markov chain. Okay, so we have defined T, we have defined Tij, transition matrix, and how did the Markov chain start? That also you want to specify. Also specify the initial distribution to start the process. Right. So, you can talk about a process only when there is a starting point. Only then can you talk about transition matrices or transition probabilities. So, that is the initial probability distribution. So, call it row vector mu. Right. So, it is again these probabilities in the range 0 to 1, and they are as many as the state space, the number of states. Moreover, you can see that the ith entry basically captures what is the probability of starting from value I, right. That is the starting point. So, immediately you get certain properties from this definition, and this is the way homogeneous Markov chains will be represented. So, first is that this if you sum up the coordinates of mu, then you get 1, right, because somewhere you will be at least somewhere, and these are disjoint events. Second is that each row or column of T sums to 1. So, what is the proof of this? The first thing, sigma mu I is the same as sum over the events x0 equal to I, but this is a partition of the whole state space, right? So, this probability is 1. That is a quick proof, and for row and columns a similar proof is there, which we will see next time. And finally, such a matrix T in general, such matrices are called stochastic. Okay, so the name comes actually from probability theory. So, matrices which are non-negative real valued entries and the row and the sum columns are 1, they are called stochastic matrices. They immediately define a Markov chain. Okay.